Okay, so time to prove some serious theorems about the exponential function. I want to prove two in this video. One, that the exponential function is increasing, and the other, that the exponential function is continuous. Each requires a lemma, so here's the first lemma. We suppose that alpha and gamma are real, alpha greater than 1, then alpha to the gamma is greater than 1 if and only if gamma is positive. That is to say, if alpha is greater than 1, then positive exponents generate values greater than 1 and vice versa. The result, if alpha is less than 1, comes from taking reciprocals. So if you can prove this, you can prove that. We're going to prove this in two directions. Let's go this way first. So we'll assume that gamma is some positive number, and we're going to choose a sequence that's increasing and positive and converges to gamma. You remember from the last video that because the exponential function is well defined, we can pick any sequence we want that converges to gamma, and it does the things we want it to do. So we're going to pick the one that's increasing and positive and converges to gamma. Then alpha to the gamma is the limit as n approaches infinity of alpha to the r sub n. So because the sequence is increasing and positive, and because the exponential function is increasing on the rationals, we proved last time that the exponential function was increasing on the rationals. It follows that alpha to the r sub k, where k is any, r sub k is any element of the sequence, any term of the sequence. We know that that's going to be greater than 1. We know that, right? Because alpha is some number that's greater than 1. It's raised to some rational number. That's got to be greater than 1. And we know that alpha to the element of the sequence, any element of the sequence, is less than or equal to the limit as n approaches infinity of alpha to the r sub n. Well, if that's the case, we know that this goes to 1 and this goes to 1. If these are all greater than 1 and these are all less than this limit, then this limit, which is alpha to the gamma, must be greater than 1 as needed. So then we go the other way, and we'll go the other way. We'll proceed by contrapositive. We'll assume that gamma is less than or equal to 0. If gamma is 0, alpha to the gamma is 1, and that establishes the result. If gamma is less than 0, then the proof of the forward direction obtains that alpha to the gamma, which is 1 over alpha to the negative gamma, is less than or equal to 1. As needed. Check. By the way, this implies that the exponential function always takes on only positive values. So it's time for the theorem. And the theorem is that the exponential function is increasing if alpha is greater than 1. Similar proof if alpha is less than 1, we get it by taking reciprocals. So we suppose that x is greater than y for x and y in the reals. If x is greater than y, then x minus y is positive. And that means that if you use that as an exponent on alpha, you get something bigger than 1. So we take a number that's greater than 1, we raise it to a positive power, that's got to be greater than 1, which means alpha to the x over alpha to the y is greater than 1. That's laws of exponents, which means that alpha to the x is greater than alpha to the y as needed. So that's an important result, that the exponential function behaves the way we hope it behaves. The other result is equally important and begins with a lemma. This lemma says if alpha is greater than 1, then the limit as x approaches 0 of alpha to the x is also 1. This sort of makes sense. We sort of figure that it is true because anything to the 0 is 1 unless that something is 0, but this something happens to be bigger than 1, so we would expect this to hold. It certainly holds for rationals. We will prove that it holds for reals. And so this is language that's going to be very familiar to all of my friends who have ever done real analysis. We're going to consider the limit as x approaches 0 from the right. The other limit is going to hold similarly, but it's a little bit easier here dealing with positive values. As with all proofs in Math 324, we let epsilon be greater than 0, and we choose an n such that the absolute value of alpha to the 1 over n minus 1 is less than epsilon. Why? Why does that hold? Well, that holds, that holds because we proved that for the rationals, limit as n approaches infinity, for rational exponents, this limit goes to 1. And if this limit goes to 1, then no matter how close you want to get, there is some n where this difference, the difference between alpha to the 1 over n and 1, this difference is less than how close you want to get. So now, as we do in all of these analysis proofs, we choose a delta. We choose the delta. The delta is the wingspan on the x values, and we're going to choose the delta as 1 over n. That's how close we want to get to this x value. And if we are within that of 0, then the absolute value of alpha to the x minus 1, which is alpha to the x minus 1, is less than or equal to alpha to the 1 over n minus 1, which is less than epsilon. Let's justify as we go. What lets us take the absolute value brackets away? Well, we know that alpha to the x has to be greater than 1 when x is positive, and so this must be a positive number. We can remove the absolute value bars. Why must this be true? Well, x is less than delta, so x is less than 1 over n, and the exponential function is increasing, so this must be less than or equal to that. And this happens by assumption. That happens by assumption. Thus, the limit as x approaches 0 from the right of alpha to the x is 1. And the other limit is proven similarly. The limit as x approaches 0 from the left is proven similarly. So time now for the big result. And the big result is that the exponential function is continuous on the real numbers. That's the big result. So here's how this goes. We're going to let gamma be a real number. We will show that the limit as x approaches gamma of alpha to the x is alpha to the gamma. That will show that the exponential function is continuous. We pick any real number, we let x get close to that, we show that the function values approach. The other way to say this that we're going to exploit is that the limit as x approaches gamma of alpha to the x minus alpha to the gamma is 0. Clearly, if as x gets closer and closer to gamma, the function values approach, the difference approaches 0, then the function is continuous. Oh, sorry. Oh, sorry. There. Notice that. The limit as x approaches gamma of alpha to the x minus alpha to the gamma is the limit as x approaches gamma of alpha to the gamma times alpha to the x minus gamma minus 1. Why? This is just algebra. There's nothing fancy here. There's nothing fancy here. And that's equal to alpha to the gamma times the limit as x approaches gamma of alpha to the x minus gamma minus 1. Well, why is that true? Alpha to the gamma is a constant. So that constant can come out and play, no problem. No problem. Well, what's happening here? Well, x is approaching gamma, so this is approaching 0. Wait a minute. We have a lemma. We have a lemma that says that this part must approach 1. And if this part approaches 1, then the whole thing approaches 0, and that's 0. And if this limit is 0, then we have proven that this is true, and so we have proven that this is true. And so the exponential function is really continuous on the entire real number line. And that's important because we don't talk about what it is to raise 3 to the pi power. We don't talk about what it is to raise 5 to the radical 5 power. But every time we graph the exponential function, 5 to the x, 3 to the x, that function is always graphed as if it's smooth. Not only that it's continuous, but it's differentiable. That's a whole other question. But we always graph it like it's continuous. We don't graph it with any holes in it. So this is a seriously important result. And I hope that you will be able to explain to students someday, hey, trust me, I've seen the math on this. this is definitely a continuous function. So we can do all the things that we do in high school with continuous functions. Okay, 15 minutes is long enough. Lots for you to process. See you soon.